Okay, hopefully we're now live. So hello everyone, thank you for attending our webinar today. My name is Russell Tora from the University of Southampton and I'm coordinator for the Wearplex project. So my talk today will introduce you to our EU Horizon 2020 funded project Wearplex, and after this we'll get on to the much more interesting demonstrations of the different technologies that are involved. So Wearplex is about the development of wearable multiplex biomedical electrodes. The project is a combination of printed electronics, e-textiles and printed biomedical electrodes for gesture control and rehabilitation applications. So this is our third and final workshop of the project, as the project ends in just a few days. So some of the demos that you'll see are literally hot off the press. We've probably finished whilst we're writing or presenting this, so hope you enjoy them. So just to give you a quick overview of this presentation, I'll quickly run through the overall agenda and then I'll introduce the project, the key concepts behind it, and along with the partners who are working on it. And I'll discuss the state-of-the-art multi-electrode systems for FES and EMG, and then discuss some key elements of this work, the printed logic circuits, printed ink development, and e-textile integration methods, and their implications for mass manufacturing. Okay, so the agenda for today, so we start with this project overview, then some short introductions from the partners and their associated technologies. We then move on to some demonstrations of these aspects and culminating in the latest gamma demonstrators for recording and stimulation. And then we have some presentations for the end user partners in the consortium on where they go next with the developments in Wearplex, and also a call for collaboration for future work. If you've got any questions or comments about any of these items or aspects as we go along, please post them in the chat, and my fellow coordinator Steve Beebe will chair a Q&A session at the end to go through these. And finally, we have our scientific and technical manager, Tierra Kelly, who's going to give some closing remarks and then give some contact details for each of the partners for any future collaborations you may be interested in. So Wearplex is a 3-year project started in 2019, and the overall aim is to integrate print electronics with flexible and wearable textile-based biomedical multi-pad electrodes. It's quite a mouthful. So the key focus points and challenges for the project are printed multi-pad electrodes with integrated logic circuits, printed electronics and textiles, and optimizing the use of high-density multi-pad electrodes for gesture control and rehabilitation purposes. So what is FES? I keep mentioning this word. So it's functional electrical stimulation. It's used to electrically stimulate motor nerves in order to activate paretic or partially paralyzed muscles. The stimulation is controlled and targeted to specific nerves to provide useful movement of a limb, so e.g. like grasping or stepping, depending on where the application is. It's used as a treatment for stroke survivors for upper limb therapy, and also lower limb for drop foot for stroke and multiple sclerosis sufferers. So a typical stimulation signal is between 10 and 100 hertz, 5 to 50 milliamps, and 200 to 500 microsecond pulses within that. So the electrical stimulation can also be used for muscle pain relief and haptic feedback as well. So moving on to which is almost the opposite effects, EMG. So EMG stands for electromyography. It's a process for measuring the electrical potential generated naturally by muscles when you move. So we specifically look at surface EMG, which is measuring the electrical activity of the skin closest to the muscle. And by measuring the EMG, we can determine the health of the muscles and their associated control nerves. EMG can also be used to estimate the motor intention of the subject, so for the purpose of myoelectric control, so almost predicting how things are going to move. And the surface EMG signal is typically in the millivolts range, with useful frequency content in the range of 10 to 250 hertz. So more electrodes provide more muscle specific information for a given movement or gesture, and this allows increased selectivity and improves the quality of the Emg recording and subsequent control. So this is kind of links in with how we're aiming to do this within Wearplex. So combining this with electrical stimulation in Wearplex will lead to improved assessment and motor intention estimation using the EMG, and better movement generation or using the FES, and again potentially with pain relief and other aspects. So why Wearplex? What are the applications for this technology? So firstly, there's a global medical electrodes market worth $1 billion. This is despite it being currently focused on lab or clinical use and not the potentially more lucrative consumer market. There are several markets identified for both wearable EMG and FES devices. So for EMG, we have human machine interfacing in fields such as gaming or drone control, smart home solutions, and assisted living for the elderly or people with reduced motor function. So muscle monitoring in general is useful for sports performance, body posture correction, and for rehabilitation effectiveness and assessment monitoring. So you see how well any of the treatments that you're doing actually, how the human body's responding to it. So for FES, you can look at neuromuscular rehabilitation. It's probably the key application to help with stroke survivors. There's actually a stroke every 2 seconds somewhere in the world, and the number of survivors is expected to be over 70 million people by 2030. So it's a huge global issue. So another application is pain relief. This is commonly already in the form of TENS machines, which is transcutaneous electrical nerve stimulation. So applying a small current to the skin near the pain to help stimulate the nerve endings to reduce the pain signals in the brain and provide some pain relief. So a more recent application has been to use FES to maintain muscle activity for patients in long-term care due to COVID or other coma patients. And again, this is helping to reduce muscle atrophy. So again, particularly important at the moment. So finally, the future target was to combine both EMG and FES to achieve electrical tactile feedback. This could be used in virtual reality interactions, haptic communications, telemanipulation such as remote surgery, and control of prosthetics with feedback sensations. And obviously, we also aim for enhanced neuromuscular rehabilitation, as a full Wearplex device would provide a closed loop feedback option for rehabilitation exercises and a more personalized healthcare, as each system can adapt to specific users. So why the requirement for this multi-pad solution? So the state-of-the-art multi-pad solutions have many advantages, such as simple positioning, because the location on the limb becomes less critical. Dynamic stimulation patterns, so you can adjust the area that's being stimulated. Reduced fatigue for the wearer caused by overstimulation of the wrong areas. And this again allows a broader recruitment level because it's adjustable. And also you get the high fidelity of EMG recording because there are more electrodes covering each muscle. So however, there are two main practical limitations to consider. By increasing the number of pads, you're increasing the number of wires that you need and limited by the number of connections you can have in your recording system. The current solutions on plastic typically have limited adherence to curved body parts. So again, these are the sort of main limits. So what's our sort of goal? What was Wearplex actually trying to do to solve these problems? So we're developing the printed logic circuitry that allows multiplexing or demultiplexing, so the electrically switching between different wires to effectively use each wire multiple times for different signals depending on what's required. So we're printing electrode pads that will be addressable into virtual electrodes, so pads can be clustered together to form larger, smaller, or specific shaped electrodes to again improve functionality. We're developing algorithms for recording and simulation to enable automatic personalization of these virtual electrodes, so that whilst all the devices look the same from the outside, they operate very differently depending on the requirements of the person that's actually using it. And if that wasn't enough of a challenge, we've also tried to combine all of this with textiles to allow much easier setup and a greater conformity to the targeted body parts. So here's a list of the project partners who've taken on this huge challenge over the last 3 years. So we've got 10 partners across Europe. So our main aim was to try and fill as much of this map as possible, but sadly our budget only went so far. So we've got 3 university partners, 4 research institutes, and 3 SMEs working together. The University of Southampton is the coordinator of the project, and the original driver of the idea was the team at Technology Serbia. The consortium has worked really well together with samples being manufactured and shipped to the next partner in the chain to add their part, making it a truly European project that's really been a pleasure to lead. So it's very good. So here are the different partners and their roles within Wearplex. So for the universities, we've got Southampton. So we were focused on the e-textile side of things. Aalborg, they're experts on EMG recording analysis and performing lots of trials with the different electrodes that have been manufactured. And Chemnitz are experts on mass manufacturing of printed electronics. So for the research institutes, we've got Technalia, both Spain and Serbia. They're experts at FES, and as I said, the Serbian guys in particular were a key driver behind this project. So, and we have BCM in the Basque country, so they're experts in printed ink development, and Rise from Sweden to bring all the advanced technology on the specialist electrochemical transistors that are essential for this work. So then we have the SMEs that are involved. So Eden, they've commercialized their biopotential electrodes that they've developed. Layer 1 was previously Avalonics at the beginning of the project, and so they've changed name, and they produced graphene oxide and reduced graphene oxide, and they're focused on scaling up these processes to make them much more accessible. And ScreenTech, who are a B2B supplier of printed electronics, and they have particular expertise in medical devices and industrial manufacturing and scale up. So each of these partners were already at the state of the art for their different technologies at the beginning of the project. So for FES, the multi-pad electrodes are typically printed on flexible plastics at Technalia, and we've done the same at Southampton on Fabricate, you can see here. So Alberg on the end, they've got 192 electrode arrays and these are made using sort of standard PCB etched copper, and these are used for reading EMG. So it's a huge amount of cabling. As you can see in the picture here, there's lots of cabling everywhere. But in each case, and similar work in the literature, the electronics are connected in separately and not integrated into the electrode structure at all. So how do we aim to go beyond the state of the art? So Wearplex is proposed to combine these multi-pad electrode structures on the left-hand side here with multiplexing circuitry printed on the electrode itself. So this will reduce the number of external input wires or increase the number of addressable parts depending on what you're actually trying to achieve. So Technalia Spain are leading the work on this control electronics and stimulator recorder, with RISE providing the embedded logic on the electrodes themselves. So these sort of parts as they come in hidden behind it. So here's an example, as I mentioned, about this concept of the virtual electrodes. This is our kind of Wearplex concept. So you can see the individual, all these grey dots are, and all the dots in there are the individual pads on the arm, and the blue and the red are examples of this virtual electrode concept. So tailoring the shape and size of different electrodes to match the user. So you can turn them all combinations of them on to form one electrode here, and then this is the blue electrode. So this example used a gesture controller for gaming. And we'll have a demo of this concept from Alberg later on. So normally increasing the number of electrode pads implies an exponential increase in the complexity of setting it up as well. So Technalia Serbia and Alberg are developing algorithms to identify which electrodes are best for each user, allowing the electrode to be personalized. So to achieve this, RISE have investigated different transistor structures to achieve the current levels needed for, so that's electrical current levels needed for stimulation and the amplification needed for recording. So demonstrators of where we've got to during this final development stage of the project will be shown later from RISE and Technalia Serbia. So as I've said, the essential component in all of this is the printed transistors. So RISE are a global leader in the development of printed organic electrochemical transistors, or OECTs, as you'll see used throughout some of these presentations. So they've used these transistors to print the control logic and the drive transistors that are needed. So these OECT devices can achieve large current throughput at very low voltages. So unlike other organic transistors, these are significantly less, or the structure is significantly less sensitive to layer thickness, which makes them much more suitable for printing on textiles, which are naturally rougher than smooth plastics. They do have a relatively slow switching time compared to other alternative technology transistors, but as this is a low frequency application, it's not a problem in this case. And FES and Emg therefore provides a really good application for these sort of transistors that have potentially been previously dismissed for other more high-end digital applications. So again, it's sort of showing that you don't necessarily need speed all the time. So to achieve all of these devices, we needed a significant amount of work on ink development on the project, with several partners involved, and this was all led by BCM. So this work is mainly to enhance the performance of each of the inks, but also to ensure that we're able to transfer to a textile substrate, giving better adherence and comfort to the wearer. So the type of inks that we've investigated, there were semiconductor inks for the OECTs, a primer ink for the fabric needed to smooth the surface, conductive inks for all the interconnects, and on top of it all the skin interface to provide good contact and transfer of energy to and from the skin as well. So to increase the comfort for the user, but also improve the contact between the electrodes and the skin, we're integrating this technology into textiles. So University of Southampton has expertise in printing electronics directly onto textiles, and also integrating complex electronics into textiles and garments via these flexible strip circuits. So we printed several different biomedical electrode devices on textiles for both stimulation and recording applications. So you can see here these are electrodes onto textile for the FES, but these are active electrodes for ECG measurement, and then we've integrated that into a what we call full Frank configuration, so you can take a full vector cardiogram of the heart, and that's using all of these are using traditional printing technology, and then this is our strip circuit. So these are flexible strips that have been woven or knitted or stitched into garments that are either during manufacturing of the garment or post manufacturing. So one focus on the project is to ensure that the inks and the processes developed in Wearplex can actually be mass manufactured. So the University of Chemnitz is focused on how to scale up the production with their experience in roll-to-roll processing, combined with ScreenTech's experience on delivery of in a commercial environment. So this process can be achieved using a modular approach with a combination of roll-to-roll and sheet-to-sheet production for print electronics. So this process is very similar to newspaper printing, if you're not familiar with it. It's essentially you start at one end and the material works its way through, either being printed, cured, or some other treatments until it comes out the end. So, okay, so before we move on to the technology overviews, just a quick acknowledgement to the European Commission for the funding of this project and to all our colleagues working on the project. So here's a photo of us locked in a very small lift just before COVID, and then unfortunately after COVID or during COVID, however you want to look at it, you know, we're unfortunately trapped in a very small laptop instead, but you know, we're still smiling, so we're getting there. So this workshop itself was originally intended to be a face-to-face event, so we can see the more wide range of demonstrators for yourself, and certainly we've got more devices than we were able to show today. But hopefully, if you see any of the partners at future events, they'll have some of our Wearplex devices to show. So keep an eye out for them in the future. So as a final plug, this is so if you want to have a look at any more details of the project and some of the publications and things, then you can look on the project website. If you join our mailing list at the end when we finished in 2 weeks' time, when we have all our papers and publications and any future information that we put out, so obviously it takes a while to get publications through, then they'll be sent out through that as well and linked on the website. So again, yeah, if you're interested, please get in touch. So next we move on to the technologies used in Wearplex. So the next speaker will be Strahini Dozen from Aalborg University, and he'll be talking about the EMG applications.
Hi, Russell, do you hear me?
Yep.
Okay, excellent. Then I can start. I guess that also you see the screen. My name is Strahini Dozen, and I'm an associate professor at the Department for Health Science and Technology in Aalborg University. And as Russell has announced, I will present very briefly the technology that we use for EMG recording applications within Wearplex project. Russell has very nicely explained the nature of EMG and you know, how this is generated, and also he pointed out that there are indeed many different applications for recording EMG signals, from medical diagnostics, for example, to sports science, biomechanical analysis, and finally control. And this later scenario is something that I will cover very briefly in this 5-minute presentation. To use EMG to control different devices, we place EMG electrodes on the surface of the skin, as you can see here, and we place several of these electrodes, which we call channels. And then in this plot here, you can see the signals that we can record from the surface of the skin. So these are the EMG signals from different channels or from different electrodes. Now, those signals have been recorded when this subject has been asked to perform different movements that are indicated here above the signals. And the important thing for you to note is that all these different patterns or movements actually produce a very different activity across channels. So those electrodes that are placed around the forearm, they measure the activity for multiple muscles. And obviously, when you perform different gestures with the hand or different wrist movements, then different muscles will be activated, and this activity will be captured by the channels. So these patterns that are related to specific motions are actually very different. And we could say that every motion has a specific EMG signature or a specific pattern that represents that motion. For example, you can compare this situation here when you have the activity of the first 3 channels with this gesture that produces the activity on a completely different channel, while those first channels are actually silent. So this is very good for us when we speak about using EMG to control, because we can use machine learning. And in machine learning, we can use a specific set of methods, which are called pattern classifiers. So we can train our pattern classification algorithm to recognize those EMG patterns and predict or estimate the movement that the subject would like to perform. In this time, we can online run this processing, and then we can actually estimate what the subject would like to do. This movement intention of the subject, we can then just translate into command signals for different devices. For instance, if you record EMG signals in an amputee subject, you can estimate his and her intentions, and then you can translate those intentions into prosthesis movements, which is very intuitive control of bionic limbs. You can also record EMGs from a paralyzed patient or from an elderly subject, even from a worker in an industry settings. And then you can estimate these movement intentions and activate an exoskeleton to provide assistance. Importantly, EMG control could actually be regarded as a quite general technique for human-machine interfacing, because if you use this EMG control, you can actually implement a gesture recognition, and you can allow or provide a gesture control of different devices, from consumer electronics, for example here, to some applications in collaborative robotics and, for example, control of avatars in virtual reality, for instance. So the field of application for this technology is really immense, and this is why also this was in the focus of the project. And indeed, there are already some commercially available solutions. This was the first device from Talmic Labs. This device is a stretchable band, and this stretchable band is simply placed around the forearm. Those modules that you see here, those are EMG electrodes. So every module is a single EMG channel. And hence, in this case, you have 8 EMG channels arranged around the forearm. And these EMG channels can record the signals that I have shown in the first slide. And these signals can then be translated into commands for different applications. Now, this is a successor of this device. So it's an evolution of the technology produced by Control Labs. And Control Labs, interestingly, have been bought by Facebook or Meta, how they are called today. And this just tells you about the potential application and interest for such a technology. The main difference between these two devices, as you can see, they use a similar design. But here you have 16 EMG channels. And now you also see the main point here that was also emphasized by Russell. What we would like is to have more channels, because if we have more channels to record EMG, we actually provide or we assess much better the activity from different muscles, and then we can estimate the movement intention more reliably. And indeed, in the state of the art, we can actually assess many channels. For example, this is an electrode that can record 64 detection points. All these points here are actually EMG channels. But the problem with this electrode is that in order to record from such an electrode, you need to use a bulky equipment, and also you need to apply gel to this electrode. So such a setup is not really convenient for clinical or for daily use applications. This is how the electrode is placed around the forearm, and this electrode provides really a high density image of muscle activity in the forearm. But as I said, the drawback is that it's not really applicable for daily life use. So this is the last slide of the presentation, and it actually summarizes or showcases the Wearplex approach, the approach that we took in this project. And it also summarizes the progression of the project. So this is how we started. We started from the state of the art that allows us to record the high density activity of the muscles in the forearm. And then our goal was actually to translate this technology into textile. And those are the prototypes that we have developed so far in collaboration with other partners of the project. And you will see some demos based on these prototypes later in the webinar. So the point here is that this translation into textile allows us to record many channels. In this case, for example, 48 channels, and down there even more. So we can achieve this high density recording of muscle activity, while our setup is actually quite compact and convenient for daily life applications. Basically, those are dry electrodes. They can be integrated into a garment. And then this sleeve is just attached or wrapped around the forearm. And in the future, you can even imagine that it could be integrated into clothes that we are wearing. So this is the setup that we have now. If you take such a compact interface and then you connect it to a wireless amplifier that allows you recording from 48 channels simultaneously, then you really have a setup which is convenient for clinical and daily life applications. And you will see some demos where this setup has been used later during the webinar. So that's all, and thank you very much.
Okay, that was excellent. Thank you very much, Strahinja. So next up we have Nicola Parinka from BCM, who are talking about the electronic ink development.
Okay, now everything should work well. So, good afternoon, everybody. My name is Nicola Parinka, and I am going to basically present you all the developments which are related to the new electronic inks, which we have been aiming during the Wearplex project. Basically, during Wearplex, we have focused on development of new inks with the three main attributes, such as inks with improved mechanical characteristics, the elasticity for textile applications. We have also focused on the improved electrical and electrochemical performance of these inks, and we have also aimed to make inks which are biocompatible for the applications where the inks come in contact with the skin. So in terms of the dielectric inks, we have developed new dielectric UV cureable nanocomposite based inks, basically with a very high elongation up to 25% and an outstanding dielectric constant of up to 25. These inks were based on the nanocomposites of titanium barrier nanoparticles with polyurethane acrylates. However, the main focus was on the development of semiconductive and conductive inks based on reduced graphene oxide. These developments we have realized together with Layer 1 and Tecnalia Spain. And within these developments, we have developed new kinds of water-based inks and solvent-based inks based on reduced graphene oxide. And we were also focusing a lot on the green aspect and green approach during these developments, so that the water-based inks are based on green solvents and water-soluble polymers, which also potentially enables the possibility of easy recycling and sustainability aspects of using these inks. And the solvent-based inks were also proved to be biocompatible, and we were able to tune the conductivity based on the different degrees of reduction of the reduced graphene oxide or changing the type. We were using the two types of the reduced graphene oxide and the nitrogen doped reduced graphene oxide. And we were able to tune the conductivity of up to units of Siemens per centimeter. And last but not least, these inks were also validated for FES applications by Tecnalia Spain. On the other hand, we were also looking at the electrochemical part of the ink, and we were trying basically to improve the electrochemical performance of these inks. And we also focused on the development of new P.PSS based inks, mainly aiming the OECT applications, where we were developing new screen printable dispersions with different P.PSS ratios, and also using the green surfactants to address the green approach. So to conclude these developments, basically during Wearplex, we have developed different kinds of new inks for biomonitoring applications, mainly based on reduced graphene oxide, and these inks are also based on green solvents and have been proved to be functional in OECT devices and FES applications. And they also accomplish the functional and processability requirements for the implementation of biomonitoring devices in large-scale applications. So that's basically a short review of the electronic inks development within the Wearplex. And I'm passing the word to the other speaker.
Excellent. Thank you, Nicola. So next up we have Abidin Kemalafi from the University of Southampton. So he's talking about the print electronics on textiles or textile integration. Hopefully.
Hello, can you see my screen?
No, you have to share it.
Yeah, done that. Can you see it now?
Yeah, I think it's just appeared. Are you on video?
Yep.
You don't have to be. I'll just put it as full screen if not.
Okay. Yes. Okay. Yes. Yep. Hello, everybody. I am Abiodun Komalafe from the University of Southampton, and I will be talking about the integration approach to electronics on textiles in Southampton. And at Southampton, we have a vast experience in printed integration of electronics on textiles. And we have also achieved a vast amount of electronic functionalities on textiles using different fabrication processes. With the printing approach, we have achieved different devices such as electroluminescent watch displays. We've achieved printed circuits, printed heaters, speakers, and several devices of such nature. In relation to Wearplex, we've also printed electrode arrays for functional electrostimulation. We've printed the Frank Vest configuration for EMG, ECG monitoring for biopotential monitoring. And these are just some of the examples of things we have achieved with printed integration of electronics into textiles. We've also explored the approach of weaving electronics component into textile using filament-based circuits. And with these, we've achieved motion sensing garments, LED displays on textile. The benefit of this approach is that it conceals the electronics from the external world. Now, screen printing directly on textile can be very difficult because of the roughness of the textile surface. To mitigate this challenge, at Southampton, we print an interface or a primer layer on the surface of the textile before printing any subsequent electronics. The benefit of this printed layer is to smooth the surface of the textile, and this considerably reduces the surface roughness of the textile. Now, what the printed material does is it fills the gaps within the textile so as to enable a very smooth surface for printing subsequent devices. As you can see on the right, the primer layer is smooth, and you can see the yarns of the textile just underneath it. It forms a planar surface on top of the textile. We've also explored the effect of different commercial fabrics on the thickness of the interface layer that is to be printed on the textile. And we've also done some in-house fabrication or custom-made fabrics within Southampton as well. The benefit of all this is to see how to optimize the thickness of the interface and the surface roughness that will enable us achieve other electronic components that is required for this Wearplex project. And so, as you can see on the right, we have a comparison between the surface roughness of a standard textile, which that we normally use here, the optic wire polyester cotton textile, and the screen printed TPU film, which is shown in red. You could see that it considerably reduces the surface roughness compared to the roughness of the textile. We've also investigated the use of laminate films. The three pictures you can see here, the first two are printed with our primer layer, and the last picture is showing the same structure on a laminated film. And with this, we can actually print our electrode. So what we are doing invariably is to compare these different approaches to enable easy integration of electronics into textile in Wearplex. We've also been sending our printed electrodes to our project partners, and we've also used Edun's electrode skin interface material to into our electrodes, so it's integrated into our electrodes, so which is showing that we are combining our materials together to achieve this functionality. And for our printed electrodes, the table on the left shows the sequence of materials we are using and their process conditions. Also, we've printed transistors on textiles, transistors from RISE, which were normally printed on plastic materials. We've transferred that onto textiles, and these have been able to be fabricated here in Southampton. And we can see here that we have a very high yield of transistors produced onto the textile, and the picture in the middle shows a close-up image of how the individual transistor looks like. And a network of all these transistors is used to form a decoder circuit, which we are also still working on, as the image on the right, which is also printed on the textile, and this is still being worked upon at the moment. When all these devices are being printed and integrated into the textile, it is necessary we see how durable and reliable these materials are. So in Southampton here, we have some reliability tests. We also use dumbbell patterns to characterize the behavior of the conductive traces that are printed onto textile. And we also try to investigate how the thickness of the primer layer also affects the electrical performance of the printed conductor. And this you can see in our papers. It would be nice to go back to our papers and see some of the interesting results that we have achieved based on this. So we do some bending tests and washing trials. And as we can see, the presence of the interface improves the performance of the electric conductors. And that is all from me. Thanks.
Excellent. Thank you, Havidin. So next up we have Katja Juncker from Eden Technologies. So she'll be talking about the skin electrode interface materials that they've developed.
Yes. So can you hear me?
Yep.
I'm going to share. Okay, can you see my screen?
Yep.
Okay, perfect.
Live now.
Welcome everybody. My name is Katja and I am with Eden Technologies. And within the Wearplex project, we were responsible for the electrode skin interface. So originally we started out as a company to develop soft reusable biopotential electrodes for, let me find the laser pointer. Here. All right. Yeah, mainly for ECG, but also for EMG. And then later on, we were refocusing on EEG, so measuring biopotential signals from the scalp. And from 2021 on, we really focused on measuring brainwaves from the ear with soft, ear tip shaped electrodes that are very unobtrusive. And in addition to that, we also came up with a full stack business plan and a full stack product, which includes the electrodes themselves, the electronics and hardware, as well as a brain analytics platform. Okay, so within the Wearplex project, we have developed a new formulation for our ink. In this case, we have actually two different ink formulations. One is optimized for biopotential recordings, and the other one is optimized for functional electrical stimulation. Our ink is a dry ink. I mean, after it's cured, so it results in a dry electrode. So it's very user-friendly. The resulting skin interface material is highly electrical conductive and soft and flexible, so it conforms really nicely to the skin. Since it's a liquid ink formulation, the processing and integration is suitable for different deposition methods, for example, screen printing or doctor blading, and depending on which application method you choose, the viscosity of that ink can also be adjusted to the process. With our ink, we have a very good adhesion to a lot of different substrates. Fortunately, also to the ones used within the Wearplex project, provided by the different partners such as University of Southampton and Technalia Serbia. And the deposition methods is also scalable. On top of that, also tested within this project, our skin interface material is biocompatible according to ISO 10993. Okay, so just before I talked about the two different formulations, you see here the black formulation for FES and the grayish tan for biopotential recording. In the lower example here, this is a textile substrate that Abiodun showed us before, with our skin electrode interface integrated. And here on top, this is a substrate from Technalia Serbia. And here on the right side, this is a huge electrode array that was provided by RISE, and we applied here our FES interface. Future developments. We plan to develop, or we have actually already started to develop a dual-purpose skin electrode interface material that is working for both the recording and also the electrical stimulation. On top of that, the material itself should be optimized for large-scale industrial production with state-of-the-art processes. For example, one could imagine making those 3D shaped electrodes by, for example, injection molding. But also the production of 2D shaped electrodes will be possible with, again, state-of-the-art industrial methods like slot die film production that is followed by a roll-to-roll punching process and a subsequent thermal lamination onto printed electrode arrays. Yeah. That's it.
Excellent, thank you, Katja. So next up is Matthias Trobak from Technology Serbia, giving us a little bit of an overview of the FES applications.
Thank you, Russell. Just let me know if you can see my screen.
Yep.
Okay, well, now I will introduce basically the second application scenario for Wearplex technology, and that's FES. Basically, speaking about FES, Russell already gave a little bit of introduction, but just to explain the principle. In principle, placing two electrodes on a human body, if we are able to control the current and the current density at a sufficient level that we can reach the thresholds for activation of certain underlying nerve tissues, whether it's efferents or afferents, we would be able to provoke the movement or to actually elicit some sensations that will be perceived by the human. So basically, this approach is very useful when you consider a matrix of electrodes. So if we consider the large number of electrodes, by controlling the current distribution through these different pads that are positioned on certain body segments, we are able to control the movement of the human. And this is this principle is heavily used for neurorehabilitation. Ideally, by, for instance, using the electrode, like you can see here in the image, by placing this integrated in the garment on top of the forearm, using the control algorithms that will distribute this current among different pads of the electrode, activating different nerves and thus also muscles. You are able to promote different movements of the hand and basically enable the subject to practice functional grasping. This is one of the application scenario, and you can see here in this video how in the rehabilitation center here in Serbia, previously we were able with this electrode with 32 pads to elicit different grasps that is enabling the subjects to basically do functional exercise, and by the means of this basically improve or let's say fasten the rehabilitation process. Similar application you can see here on the left is drop foot. Basically in drop foot this can be considered not only as a, let's say, as a therapy, but also as a system that can be used as a permanent orthosis for the subjects after stroke when they are not able to lift the foot accordingly during the gait cycle. A system like this, comprising one of these matrix electrodes, can be used to basically promote the complete, let's say, cycle of the foot movement. For instance, the lifting of the foot, but also the pressing of the fingers. TENS is another application for the electrostimulation technology that can be used for different, let's say, aspects, but most primarily for treatment of the pains, for treatment of pain. And you can see here in one image on the top in the video, this is used in one of the systems that Technalia developed to basically numb the pain in the elbow and promote this functional movement. But there is also this other application down below where you can see when this matrix of electrodes is basically used as a massage of the back to loosen up the muscles there. And then the one more application that is of interest for the talk today is this electro-tactile feedback. In one of the previous projects, Technalia developed the system that is using this electro-tactile feedback technology, array of electrodes to present the feedback from Michelangelo hand during the for the amputees, basically to be able to perceive what the hand is doing, but not necessarily to have to look at the prosthesis, but to already know what are the movements, 3 degrees of freedom, so both the control of the aperture, rotation of the wrist, and the flexion extension of the wrist. This was all coded by using this matrix electrodes. So the number of the electrodes that we are able to control is very much important, and this is why the Wearplex technology is crucial for FES application, because there is clearly one of the limitations that we noticed in the let's say state-of-the-art systems, and this is basically the number of channels that we can control in terms of, or not that we can control, but that we can interface, because clearly there is the physical barrier in terms of the interconnection between the hardware, as you can see here, that is connected to the electrode. So to enable that the electrode can contain larger number of pads and to, well, basically reduce this strain in terms of the interface that is included there, we recognize this embedding of the, well, of the logics, that is the multiplexing logic into the electrode itself, to enable us to achieve large number of pads that can be controlled by this system. And there are two, let's say, application scenarios that we recognize, that we identified will be of interest to basically demonstrate the Wearplex technology. One is this tense-based application, where you can see here the one, let's say, we call it like kinesis tape. Kinesis tape that is embedded with electrodes that can be used for this tense application, so large number of pads there. And the other that we can consider of interest, of target, and that you will see later in the demos, is the electro-tactile feedback technology. So using this to achieve even larger number of pads that will be integrated into some type of a sleeve, and then to present this as a feedback, is of great interest. And here is what is the current status. Basically, last year in the beta stage, what we were able to demonstrate, what we had developed, was the OSCT device logics that were 2 to 4 based on 2 to 4 decoders, and with this we were able to drive 16 pad electrodes, as you can see here in the image on the left. We advanced in the gamma stage and developed basically 2 demonstrators. Rice developed the logics, and we developed basically the hardware that allows us to test this for electrical stimulation. And one device is 8-bit shift register that is intended as this tense electrode. You can see it here on the left, on the top, in the middle actually, and on the bottom you can see 3 to 8 DEMUX electrodes that we envisioned as a use case for electro-tactile feedback. On the right, you can see the testbed that was used basically to connect these 2 electrodes and to test them. And in the demonstration later, you will see how this worked. This is it from me.
Excellent, thank you, Mattia. So next up we have Peter Andersson Ersman from RISE in Sweden, and he'll talk about the OECT devices that we keep mentioning.
Yes, can you hear me?
Yeah.
And can you see my screen as well?
Yes. I'm just trying to get your video on.
Great. All right. Yes. So my name is Peter Andersson Ersman. I represent RISE, Research Institutes of Sweden. And you also see the names of the team here at RISE who have been active in one way or the other in the Wearplex project. Josef, Lars, Catherine, Jan, who have been responsible for one package each, so to say, within characterization, design, and printing. And then also Jessica Marie and Navid, who has been active in the printing lab. So this is first an introduction of the organic electrochemical transistors, or the OECTs. In the top images, you see the cross-sectional view and also the top view of the devices, and it's a relatively simple device, and this is also why we are able to screen print the full structure of the standalone devices, but also the full circuits. In principle, you need a substrate, which is omitted in the schematic, but it, as you heard, it could be textile or paper or plastic, for example, or any other flexible substrate. And then we screen print. To get the functionality, you need these layers, the channel, which is typically P.PSS, source and drain electrodes, electrolyte and gate electrode. And then, of course, to create circuits and more advanced circuitry, then you need some other layers as well, like insulators and metal layers and so on. These are the fundamental layers to create the functionality or switchability. They are electrolyte based, which means that you get very low voltage operation. You only need approximately 1 volt to fully turn off the devices by 4, 5, 6 orders of magnitude. These are said to be, PEDOTPSS is a P-type material, and it's conducting in this pristine state, which means they work in depletion mode. So they are conducting at 0 gate voltage and non-conducting when you apply the gate voltage. The pristine conductivity also means that you have very high current throughput because you drive the current through the whole bulk or the whole thickness of the channel, which makes them very useful in applications that requires high currents. It's scalable manufacturing. As we've seen already, we can do this by screen printing, sheet to sheet, or even roll to roll. And yeah, they're of course promising in many application areas, in any kind of logic circuitry. And here in this project, as you will see, we use them for the recording applications or the stimulation applications. But it's very popular device as well to use in various kinds of sensor applications as well. Yeah, I'm not going to go into the full details here, but if you have this P-type depletion mode transistors and you combine it with a resistor ladder, you can create, in principle, any kind of logic circuit. Here I show inverters and 2-input NAND gates. And with that, you can actually create a lot of other, even more complex circuitry, which you see in the images and schematics at the bottom. You see shift registers and also decoders to drive, for example, the electrochromic displays that we also developed at Rise. And since they are based on the same materials, you can actually monolithically integrate them onto the flexible substrate in the same process by printing the same type of materials. Yes, and this is about a little bit about the reproducibility. As you can understand, we are targeting these multipad electrodes in Wearplex, which means that we also want high reproducibility in the UCTs, both for the logic circuitry, but also for the UCTs responsible for recording the Emg signals or the or passing through the stimulation current pulses. Top right image shows 5 different UCTs where the curves are laying perfectly on top of each other, both the drain current and also the gate current. And these devices are taken from the sheet at the bottom right, consisting of 760 UCTs, where two of them were malfunctioning. So that gave a 99.7% manufacturing yield. As I said, the bottom left, we can combine the addressability by building different kinds of decoders, multiplexers, and shift registers, and combine it with the high current throughput here, exemplified by showing the truth table of the decoder by light emitting diodes. And the most recent publication is actually a combination. It's a novel processing method where we combine vapor phase polarization with screen printing, which here shows almost 6 orders of magnitude in on-off ratio in dynamic switching mode. And the highest current we saw was 60 or 70 milliamp, which is remarkably high for being an organic-based transistor. So within Wearplex, you already heard both Russell and Mattia talk about the applications a bit. The target is to develop these printed circuits into the multipad electrodes to minimize the number of wires or input-outputs on the addressing electronics. And preferably, they should work in both directions, which means both for recording and stimulation applications. What you see in the images at the top, you see one or a couple of the kernels for the stimulation application, which is based on an 8-bit shift register. And at the bottom, you see freshly printed decoder circuits for the recording applications, where each kernel is based on an 8-channel multiplexer circuit. But more of this later on, so I'll leave it there. Thank you.
Excellent. Thank you, Peter. So next up is Nicola to talk again. This time about something that we haven't actually mentioned so far. This is the human model equivalent circuit that they've been developing.
Okay, thank you for the word, Russell. Basically, I am going to give you some brief insights of what has been the development of printed human equivalent circuit, which was quite a significant development within the Wearplex. Basically, the development of novel large-scale flexible fast electrode and devices needs a large number of trials on human subjects. So that's why we have decided that we would like to also develop some system which could at least reduce or maybe even replace these trials, and also not using the traditional rigid electronics, and move it rather to something printable, flexible, which is representing in a better way the behavior of the human skin. So basically, we have based our concept on the standard equivalent model of the human skin, which is based on which is represented on as a sequence of capacitors and resistances, which are basically representing the interface between the skin and the electrode. And we have converted this circuit into a printable design, which was later implemented by means of a screen printing process, which you can see on the slide. Basically, we have created a sort of stack of a multi-layer based on different materials, such as conductors for the electrodes and leads, dielectrics for the capacitors, and the semiconductors for the resistances. And these were printed in a sequence of 5 layers, each on each, so that at the end we have received a sort of flat testbed printed on a flexible PET. And we could use that device for testing the multiplexed electrodes which we have developed during the Wearplex. I should also know that the design was modified according to each stage of the project, starting from alpha demonstrator, going to beta, and last but not least, gamma. But as you can see, more or less it's based on the same concept. And later my colleagues from Technaria Serbia will explain how it actually works and how it can be used for testing the electrodes which have been developed within the Wearplex. So that's just a short explanation of the background of such developments from my side.
Excellent. Thank you, Nicola. So next up is David Holzner from the University of Chemnitz talking about scale-up printing that they've been working on. You're muted at the moment, David.
All right, now you should
hear
hear me, and I hope you can see my presentation as well. So yeah, my name is David Holzner. I'm working at the Institute for Print and Media Technology at TU Chemnitz, and our task within the Wearplex project is to develop a printing process and also develop a strategy for upscaling this printing process. So in very few words, our institute has many years of experience in different fields of printed electronics and also large scale printing. Excuse me for a minute.
should be able to. Oh, you should be able to click the little button on the bottom corner.
Does it work now?
No.
I'm sorry.
Just where your pointer is now, go down a little bit, and there should be a little thing that looks like a blind you're pulling down. If not, just show it as it is. It's fine.
Okay, I'll just go ahead like this. I can't fix it
It's fine. It's
at
fine.
the moment. So you can see the slides, right?
Yep.
All right. So yeah, I'd start over again. So I'm working at the Institute for Print and Media Technology at TU Chemnitz, and we were responsible for developing a printing process and also the upscaling strategy for such a printing process. And our institute has many years of experience in different fields of printed electronics and also large-scale printing of printed electronics, such as printed solar cells, supercapacitors, paper-based loudspeakers, and many more. The upscaling workflow consists basically of 4 steps. First, a lab scale where you print on simple single sheet test printers to get a general idea of the printability of the different functional materials. And then from the data you gather at your test printers, you transfer this to semi-industrial roll-to-roll printing line. And finally, we can give a good guideline of how an industrial line for mass production for the Wearplex device would look like. So in the lab scale, we evaluated the printability of all the Wearplex functional materials involved, which are some of them are commercially available and some of them were self-mixed by different project partners. And during this process, we mostly focused on screen printing and also with a focus of a later transfer to a roll-to-roll screen printing process. And from all this test printing, we developed kind of a manufacturing recipe, which includes data for all the materials involved, their printing, pre and post processing parameters. And in the next step, we moved from our small scale test printers to an actual semi-industrial web-fed line, as you can see on the bottom left, with a rotary screen printing unit. But this line is also capable of combining different printing technologies, such as gravure printing or flexo if needed, and it is flexible in the post-treatment, whatever your material requires, infrared, hot air, or UV treatment. And with this semi-industrial line, we managed to demonstrate a fully roll-to-roll screen-printed electrode stack of the Wearplex device, and we managed to fine-tune some of the printing and post-treatment parameters in such a roll-to-roll process, and we identified some of the critical requirements for mass production. And we also took a look into other roll-to-roll production methods, since actually all layers of this Wearplex stack were printable in rotary screen printing, except for 2. They were causing a little trouble in this screen printing method, so we evaluated alternative mass production or mass printing methods for those 2 materials, being gravure printing for P.PSS. You can see a a picture of our gravure printing test stand on the bottom left, and also took a look into slot die coating unit for the skin interface material developed by Idun. And finally, we developed two different strategies for how such an industrial manufacturing line could look like. One being a web-fed roll-to-roll printing press similar to the line that we were using, which has a benefit of being very efficient and high throughput. And with a drawback that I just mentioned, that two materials were causing a little trouble, and they would need a little further refinement in alternative production methods, or alternatively in the material development itself. So we showed the possibility of a second industrial manufacturing line, being a flatbed roll-to-roll or roll-to-sheet line, which would have the drawback of being a little slower, since it's basically a stop-and-go process, but with the benefits of being much more flexible in the printing for materials, such as you can also use PET screens, and you can use stencil printing or doctor blading. So it's very versatile, and it would also be possible to handle all included Wearplex materials in such a line. And a line similar to this is actually currently employed at our project partner, ScreenTech. Yeah, that's it from my side. Thank you.
Excellent, thank you. I've just got, if you hang on 2 seconds, because I've got your presentation working, and I just wanted to show the video because it's really good. So hopefully.
Oh, perfect. Thanks. Yeah, this is cut together some short sequences of the roll-to-roll printing process at our semi-industrial line, starting with the primer layer developed by University of Southampton, different curing technologies, followed up by silver layer printed on the primer, followed by infrared drying unit, and subsequent printing of the carbon material on top of the silver. And finally, the dielectric encapsulation layer. It's a bit hard to see because it's white, printed on white, but it's there. Right. Thanks a lot, Russell, for jumping in.
Excellent. There's such a good video, it had to be seen. So it really shows just how complicated it is to actually make these production line, and just how big all the equipment, and that's only a very tiny system relatively to big industrial ones. So okay, so next up we have the demonstrations of the different Wearplex technologies. So we've laid this out as effectively telling a narrative of how we started off with the Fabricate integration and the what we'd call passive systems with the Emg Recording, and then adding in the OECT technology that we've talked about to end up with the much more complicated and truly Wearplex based electrodes at the end. So Aberdeen is up first from Southampton to talk about the Fabric integration.
Hello, can you hear me?
Yeah, it's quite quiet, but yeah.
Okay.
Yeah, it's better.
So once again, I'm Abiodun. I'll be going through screen printing and integration techniques in Southampton. And since most of our work has to do with textiles, so I'll be focusing on the techniques we've been using to integrate electronics and textile. And it's quite a nice video we've just seen from Chemnet, and we'll be seeing how we've been doing it in our own lab also. So one of the main technologies in Wearplex is screen printing, and this is how we try to first smooth the surface of the textile before printing any subsequent electronics into the textile. And to do that, we load our screen with the primer ink, and which we subsequently print on top of the textile. And we ensure that the ink is of the right viscosity, and so that it's when it's being flooded on the screen, it's being able to be pressed onto the textile without having any difficulty. So after this first layer printing, we repeat the process for subsequent layers. So we cure it after printing. And this is cured with the UV light for 30 seconds. And after curing the printed ink, we repeat the process all over again for other layers, so until we achieve a very smooth surface. So this is actually one of our commercial fabrics, which requires thicker layer of primer layer to be printed. And in this case, we are printing up to like 5 layers. But for the optic fabric, it's just 4 layers that was printed, and it achieves very smooth primer layer on the fabric. And one of our custom made fabrics also, we just needed 1 primer layer to be printed on it. And so we also looked at the woven integration of electronics, which is helping us to link the printed electronics with the connectors that we will be using to connect all our electrodes together. So this video is just showing us an approach where how we intend to conceal the flexible filament into the textile. Having fabricated the filament using photolithography and etching and mounting the necessary components, the filament is integrated into the textile during the weaving process. We hope in the future that this process of insertion of the filament will be automated, and once that is done, the wires is also routed in the pocket, and the pocket is closed after the filament is integrated, and that is how it is concealed within the textile. And next up, we also look at the durability test of our samples, ensuring that they survive practical stresses in real applications. So, so this is one of the dumbbell patterns. So we subject them to bending test, and we have the Wearplex electrode as well. We vary the bending radius as much as we can, and we can also make in situ measurements during bending, taking the measurement from a multimeter controlled by a LabVIEW program. And how then do we integrate the electrodes into textile? So this is just an example integration. So in this case, we have printed electrodes on laminates after printing them. Another one here is the printed electrode on textile directly. So this is the sleeve upon which the electrodes will be integrated. And we have the backside of the sleeve showing the pockets for the connector circuit. Now we have the textile, which is meant to be stitched onto the sleeve, and we also have the laminated electrodes directly onto the sleeve. And in this case, we have both integrations together. After integration, the electrodes are flexible, they are bendable, and they can be stretched, which is one of the benefits of this integration approach. And you also have the connector carefully concealed within the fabric. And to finalize this, it is easy to wear, and we have it been strapped onto the arm for ECG and EMG recordings. And this will be forwarded to our partner in Aalborg, which is going to show you in later a video of how this actually works. And so early approaches of us trying to test printed electrodes. This is actually a crude demonstration just to show the principle. So we are combining the printed electrodes with the woven structure. So in this case, you have the haptic feedback that we have the printed electrodes there on the left, and the motion sensors are also stitched onto the gloves on the right with the high voltage simulators and the multiplexers just beneath it at the wrist region. And this is overstitched to ensure that the electronics is not visible to the world. You could see it's still very crude. It's still just showing the principle. And this can be improved with the previous weaving technique that I showed earlier on. And everything is completely stitched together to make it more presentable. And this is a video of it actually working. So as the user moves their hands, they get some feedback sensing, and you can also see it using it to control the image on the screen. This is the other part of the Wearplex, Wearplex projects, trying to put transistors on the textile to switch between electrodes. And in Southampton, we've been able to print the OECTs, which Peter will show more about later. We'll put it on textile, and we've been able to demonstrate it switching and turning off the transistor to turn on an LED, as you can see at the right hand here. And this is what we've done, and complex integration of this is still underway and will be shown later. Thanks.
Okay, excellent. Thank you very much. Just so if anyone is interested, nearly all of those hand models are available for other advertising needs. Just get in contact. So next up, we've got the Emg Recording system from Louis at Aalborg. Hopefully.
I'm gonna share my screen now. Yeah, well, hi everyone. I'm Luis. I'm here to present you this demo for Emg Recording using Wearplex electrodes. And for this, we prepare a video so that it will showcase two scenarios where we can use the Emg-based control. So what I will do is just play the video, and I will talk over the video so that you can explain you what you are seeing. I'm gonna start now, but yeah, now you should be looking at the Aalborg University logo. If that's okay, then I will continue.
Yeah, it's working.
Nice. So let's start with the setup. This is a bit a summarize of what you're saying before with Abiodun presentation. So this is just the 3 different prototypes or levels of integration developed at the consortium of Wearplex. As you can see here, we always use this configuration of 3 matrices in a row so that it allows us to wrap it around the forearm so that we can just collect the data from different muscles from the forearm, because we want to estimate the moves of the wrist and the hand. This last prototype is kind of a modular design where we can just mount and dismount the matrices individually. So it's kind of convenient in the case that we need to replace them because they were worn out or whatever reason. And still we can just keep the armband. It was designed as University of Southampton, as you've seen before. And this is well, the prototype we will use for the demos is in this configuration. And now you can see just a quick setup. So once we connect the cables in its matrix, then we just wrap it around the forearm with the Velcro straps, and then we use the connector and we connect it to this wireless amplifier that the user is wearing on the arm, which communicates through via Wi-Fi to the computer, right? So at the end, those are all the cables. The cables that you see on the screen, that's all the cables we used during the setup and during the demo, actually. Now we are ready to go. So I say we have two showcase scenarios. One of them is going to be this virtual joystick, in which the user will actually control a cursor on the screen. This is this green dot using the wrist. So the wrist will be as a joystick, right? How do we do this? So as usual, first we do is to collect the training data. So we ask the subject to move the wrist left and right, following the cursor. So it has to be on synchrony with the cursor, replicating the moves. In this case, it's going to be like an extension of the wrist and a flexion of the wrist for moving left and right. Now we do the same up and down. Okay, so we have 2 degrees of freedom, we call them. And again, for up and down, it's going to be deviations of the wrist. So we collect this data while the subject is performing these moves. We process it, and then we train a regression control, a model, using machine learning. And then it will estimate the position of the cursor by measuring the activity of the EMG. As you can see here, now the subject is controlling the cursor in real time. So it has to follow these blue circles and get inside. So one of the advantages of this regression control is that you can move not only left and right, up and down, but actually you can activate them simultaneously. So if you go down and left, you will produce a diagonal, as you can see here, even though we didn't train in that position, right? So the system is able to predict or to estimate also combinations of both degrees of freedom. And this is very intuitive because the subject doesn't need to train in every single position. Now this is just a speed up video, so you can see all the directions it can go. So with a short training phase, you can move freely around the whole space by combining the 2 degrees of freedom, in this case, left, right, up and down. Yeah, this is an application, let's say, for virtual reality or just interfacing with a computer. And then we have a second application, which is also kind of common, and it's just using to control a physical device in this case, right? So in this case, it's going to be this exoskeleton hand, prosthetic hand. So in this case, the subject is actually controlling a left prosthetic hand with the right hand. Okay, so the control is mirrored. So the hand is going to mimic the hand of the subject. Okay, and again, we have 2 degrees of freedom. In this case, it's going to be the pronation and supination of the wrist. So you can rotate left and right, and also the hand, it can open and close. Okay, so those are our 2 degrees of freedom that we call them. As you can see, you can just open and close. That will be 1. And also you can do the rotation. Okay, you can rotate left and right. But again, we can activate them simultaneously. As you can see, you can rotate and you can open, right? Despite the fact that the user only trained rotating and opening, closing individually. So this is kind of convenient, and especially is very natural from the point of view of the human motion. And here, this is the second advantage of this control we call simultaneous and proportional control. The proportional part is because you can modulate the force by the force that you are set is proportional to the amplitude of the EMG, right? So then you can do different intensity of grasp. In the case of, for example, you are controlling a hand, you want to control the force because you don't want to break an object which is fragile, let's say. So here you can see this is kind of half of the grasp. And if the object is very heavy, you want to do a strong grasp, right? So you can modulate this force because it's proportional to your EMG. Okay. Here this is like a full grasp. And now we are going to see a practical application or a functional task. Let's say. Let's pour some water with the bottle. So here we don't want to squeeze the bottle, so just grasp it. And also we want to activate each degree of freedom individually, so we don't lose the bottle, right? So that's the advantage of the regression, that you can, yeah, there it is. You can do both simultaneous and individual control. So this is not always working, but most of the time it does. But that was it. So thanks for watching. I hope you enjoyed.
Excellent, thank you, Lewis. I'm disappointed you didn't crush it at the end, but that's good. Okay, so next up we have Milos Kostic from Technelia, Serbia. So he'll go through the stimulation testbed.
Okay, I hope you can see me, and hopefully very soon you will be also able to see my presentation for real. No? Maybe now?
Yep, see acknowledgements page.
I don't know why. Okay, so I'm Milos Kostic from Technelia, Serbia, and I will show you now the testbed for stimulation, but also for recording, in the sense that how we can test the electrodes if they are working, because as you saw now, the actual technological complexity of the electrode is now much higher than before, and we have all these electronics inside, and it is very useful to make sure that they are working before we can do such cool things like controlling the hand, like Lewis showed. So these are the two things that we will show. First, how the stimulation system looks, and a small demonstration of the stimulation system in action, and also the analog system for testing of recording electrodes. Now, this is the example of the stimulation system testbed. So here we have the stimulation electronics, which provides generation of the stimulation pulses and controls the signals for the OECT logic. And here, this entire screen or page is a sheet of printed gamma electrodes. So here we have a number of electrodes, and this one is which we will be testing in the video that I will show in a minute. Here we have the human model equivalent circuit, which is exactly like the one shown by Nicola, just this is the non-printed version. This is the version that we can use when we are testing just the electronics without the pads added, like we are doing here. And also we have the oscilloscope probes that are connected to these different test points of interest, because in this version of the human model electronic circuit, like in the printed one, we have many points of interest that can be easily connected to the probes. Now, what we want to see and what we want to check, and what you will see in the video, is how these OECT circuits can control the current propagation between different channels. Also, how we can achieve switching from one channel to another one, and we will also see when we get a negative result, or when we detect that there is actually a current leakage. So instead of current going just through the designated channel, it also passes through another one. So here is the setup. We also added this humidity control chamber. It's a high-tech device made in-house, because humidity is quite important in these prototypes. So here we can see in the channel 1, which is presented in magenta, which has most of the current, where there is slight leakage on other channels. And now when we switch from channel 1 to channel 2, you can see that slowly the current shifts, and now it is all in green, which is working quite nicely. And now we can see the switch from 2 to 3. And this relatively slow switch is actually a feature in electrical stimulation, because this is quite good for some physiological phenomena that we want to see. Now here we have a channel in blue that we are slowly increasing, and then it appears that there is a current leakage between 5 and 8. Now instead of going all through one channel, like here in channel 7, which works perfectly fine, and all current goes there, when we switch now to 8 again, you can see that for some reason the logic of this specific electrode is faulty, and 6 and 8 are short-circuited, and you can see that half of current goes through one and half through the other. Now I would like to show this all again, because maybe you didn't catch it the first time. So here we have when it is working properly, and we have the current going mostly through channel 1 with small leakage in other channels. And now when we switch, we see that the magenta is going down, the green is going up. And now even more beautiful switch, I mean better recording, where we can see in real time how the channels are being replaced, so how we are going from 2 to 3. Now, as Luis also noted, it does not work every time. So here is the example of an error or faulty electronics, where the channel 5 has a leakage together with channel 8. And the channel 7 works fine. When we switch to channel 7, you can see that all current goes there. But then again, when we go to channel 8, you will see that actually half of the current goes through the channel 5, which we saw, or channel 6, sorry. I don't know. In one of these two captions, I actually made the mistake. I'm not sure in which one. So this would be how the testbed works, and this would be, let's say, one set of results that we got when testing one batch. So for example, when testing at voltage of 20 volts in the amplitudes of 1 and 2.5 milliamps, we can see that there is always some leakage, but normally it is quite negligible. So between channel 1, majority of the current goes through the channel 1, while the rest is distributed through all other channels. But since when we look at it practically, the amount of current that goes through the other channel is physiologically negligible, or it will not produce any significant results, we can actually say that this device is working quite good for all of these channels, because majority of the current goes through it, and there is no other channel where a similar amount of current would pass. Now, analogous to this, we also had to make a testbed for the recording system, which is slightly more simple. So here what we have is the testbed that is both recording and generating a signal, and the signal that we are using here is a simple sinusoidal signal, and here we can see an electrode that is actually integrated into the textile, and later my colleague Mattia will show you several more electrodes that were integrated like this and actually made into garments, as you could see in Luis's video. Now this specific electrode is the one that we will be testing today or in the video. And here actually we are just going with the probe from channel to channel to check how the signal is working. And what we want to see in this video is how we can control current between channels, how switching between channels works in this this type of device for the recording, how we can get a result where in some channels the signal is dampened by the imperfection of the OECT circuitry, and also we can find if some channels are slow in switching, and all of this we will see now. Now, sorry, we had a setup in vertical because it was just more convenient. So you can see now we are watching it as signal at channel number 1, which you get full sinusoidal signal, while in all other channels you can see that there is actually no signal is passing, so basically there was no leakage. Now channel 2 actually takes some time to go to it. As you could see in the beginning, there was some signal first on channel 1, but then it went to channel 2. Now you can see that on channel 1 there is a lot of signal, on channel 3 nothing, but we want to have signal on channel 3. This is an example of a slower switch. So basically it takes some time for the channel 1 to get closed, or actually for the channel 3 to open. And you will see that as the time progresses, the signal on channel 3 becomes higher and higher. 1 is now already gone, and now we have significant signal on channel 3. No other channels are conductive, so there is no leakage. Now in this one, we can see that when we turn on the channel 4, there is a slight problem. The channel 4 is actually not conducting the entire sinusoid signal because there is some dampening of the signal. And it just never reaches more than these like 70%. On the other hand, the channel 5 had an issue where the switching was very long. So you can see here that there is no signal in the first pass. No other channels are also showing any signals, but you see that it is slowly building up, but it actually takes a very long time to switch on. Now, this is not a problem per se. It is not the ideal system, but also if we are just aware of this situation and that the device is characterized, then it can be mitigated. Or if it takes too long, we can just say that the device needs to be discarded. Now at this stage, the test bed is manual. As you can see, we are moving by just touching with the probe each channel, but actually it is fully enabled for digitalized channel. Now just to check again how when we turn on channel 1 very fast, you can get a full signal on channel 1 because that was the one that was working perfectly. And more or less that would be the whole video. Now you can see that the signal is fully transmitted. So that's it, yes, and these are the acknowledgements and the contact, but I'm guessing that you already saw that in earlier presentations. So that would be it from my part. Thank you.
Thank you, Milos. So I actually got the wrong, it was supposed to be Peter next talking about their ACT, so I'm sorry about that. So Peter's going to go back and show his slides, which hopefully make makes Milos talk slightly more sense. Peter's there.
Yes, I'm here. All right, so can you see my screen?
Yep, working.
Very good. Yes, so in the previous presentation, I was talking a bit, I gave a little bit of introduction to the OCT technology. This will be a bit more towards what we've done within Wearplex. And as you already saw in the presentation by Milos, he was testing some of the 8-channel multiplexes for the Emg Recording. This is the design. To the right, you see the full sheet. So it contains 24 kernels with 8 pads each. So 192 skin electrode pads in each sheet. And the left image shows a zoom in of one group of 4 kernels, just to give you a hint on how they look like. Each 8-pad kernel is based on a 3 to 8 decoder circuit plus 8 of these drive OCTs. So in total 38 OCTs per kernel. The stimulation application is instead based on an 8-bit shift register. It is much more complex circuitry. So each kernel consists of one 8-bit shift register, and that contains 156 OCTs. And this also explains why it's much more difficult to get this to work properly. The schematic on the right shows the full sheet containing 6 of these kernels and a total of 48 skin electrode pads. But this requires approximately 1,000 transistors in one full sheet. So those are the designs that we have been working with in the gamma stage. And as I mentioned before, every single step here is based on screen printing. So here are a few videos showing the different layers, just a few of them. It would be a bit too boring to show all. In the beginning of this one, you will see how in the lower left you saw some movement, and that was the substrate that's moved in from the left, and then you do the printing. In this case, it's an insulating layer just to protect the devices before we continue with the printing of some other layers. And then in the end here you see the substrates moving out on the right hand side instead. And then it can be picked out for curing either by UV light or by thermal means. Next layer is probably silver, and maybe I can stop it here, for example. Oh, sorry. So these are the recording circuits, and maybe you can see the shape of these kernels, and that you have 8 very small tiny circles, and those are the what eventually will become the skin electrode pads. And finally you have this one, which is yet another insulating layer. So all the yellow areas is where you push the ink through, so that will become insulating. But then you have you see maybe those circular shapes or dark spots inside here. This is also the recording circuit, and those are where we have those silver pads that will come in contact with the skin eventually when you run it in the recording application. So that's sort of how the screen printing process look like for some of the layers. And yeah, a little bit about the 8-bit shift registers, which we use for the FES or the simulation applications. As you heard before, we want to embed or include the logic circuit inside the actual multipad electrode instead of having the logic outside. The purpose is to minimize the number of addressing lines into the circuitry. And here you can see a few images, and then you see in between all these huge silver pads, you can see some printed features, and they are actually laying in some layers below the silver pads, and that is in this case the 8-bit shift registers. And we have been working with in this project 3 different substrates. All are flexible, and it's plastic, just standard PET, and then also TPU and also the textile. But as Abhiudan mentioned, we are not printing directly on the textile because it's simply too rough surface. But we use the interface layer that has been developed by University of Southampton. And what you see here are a few examples of these shift registers that have been screen printed on the textile substrates. The recording circuits, the same thing here. We have also been using plastic TPU and textile for these. The 2 images to the left are printed on textile, and the ones on the right-hand side are printed on PET foil. A little bit on the characterization. This is one way to characterize the circuitry. As you heard Milos, they developed this testbed circuitry. We are instead using more standard parameter analyzer, SMUs, source measure units, and oscilloscopes to do the full characterization of the circuits. And just a bit of zoom in on the. So I'm not sure if you can see, but normally we use these SIF connectors to minimize degradation or delamination of printed wires when you insert them into the circuitry for characterization. Sorry. And here to the right, you also see another example of some printed circuit boards where we use these SIF connectors to, in this case, test the recording circuits of the gamma stage of this project. This is a video shot from a 4-bit shift register in full operation, and if we start it, you see on the top, you see the clock signal, and then the red below is the data input signal, and then the four lower ones are the Q1 to Q4. In each one corresponding to a respective flip-flop circuitry. In the beginning, it's just random things because we haven't put anything into the data input. And when you run it, you now see soon there the very first input, and that gives you a high on Q1, and this is then shifted in a nice way to Q2, Q3, and Q4. And then it starts all over again with another high on the data input, and then it's shifted through the circuitry. Yes, so this simply shows the full functionality of a, in this case, 4-bit shift register. I mentioned before that RISE is also developing electrochromic displays based on the same materials, which means that PWSS, when you change the oxidation state, you change not only the conductivity used in the transistors, but you also change the color or the transparency of the material. So this is an example of the same shift register, but looked via a microscope. And you can disregard the 2 things on the right, it's just too confusing, but the NAND up here controls the driver OCT. And I will not show the full video, but if you go here, for example, and click, for those of you who remember the high school electronics, might remember that a NAND gate always is 1, except for when both inputs are 1, then it becomes 0. So here we have inputs 1, 0, and you see a blue color here, which means that you have a 1 on this one. If you run it for a few more seconds, sorry, it doesn't work. It worked before to do like this. There. Oh, I'm sorry. I think we have to skip this. Anyway, there's one way to also visually detecting. It's quite fun to see how the color changes when you do like this. What is then ongoing towards the end of the project? As I mentioned, we printed these, both the 8-channel multiplexers and also the 8-bit shift registers. They have been characterized, but then we also printed a new batch on textile last week, and they are now being characterized as well. And this is just a teaser of this, and so far we have not found any fully functional shift register. They are simply a bit too complex, but we have seen that 7 out of 8 flip-flops are functional, so we can at least control parts of the circuit or the pads. But quite many of the 8-channel multiplexers are functional for the recording. And here you see the layout and a photo of the printed circuit. And also to the right you see, similar to what Milos showed just a few minutes ago, where we input on high 100 millivolt peak-to-peak sinusoidal signal at 1 Hertz to our initially closed channel, and you see nothing, and then you open the channel and you see the full amplitude, 100 millivolt, and then you close the channel and then you see nothing again. So it looks very, very promising, I would say. So yes, thank you for that. I think I'll leave it there.
Excellent, thank you, Peter. So the final demonstration videos from Mattia Strabak in Technology Server showing the complete system parts that they've got.
Thank you, Russell. Hopefully you can see me. Well, this will not be a presentation. Actually, I mean, this will be the closest to demonstration that you'll get there. Clearly, we needed to prepare, and as this is not a live event, we can't really demonstrate this Electro-Tactical or FES capabilities of the system, because for this we would need to put the electrodes to skin and really have these immersive effects. But speaking about what is the idea of this final conclusive remark is to show you basically where we came with the system in comparison to the demonstrators that we outlined previously. So if you remember, we had the idea to develop one electrode that will be embedded into let's say a wristband, and the idea for this is that there are 2 target applications. One is this Emg that you saw basically in the presentation from Lewis and Alberg, how this is used for controlling the cursor and controlling the prosthesis, and many different applications of the high density Emg. And the other means of using the electrode that is of this type, so high density smaller pads, is to be used for electrostimulation for the tactile feedback. And then there was this other targeted applications that you saw that was in a form of, as we set in as a target of tense electrodes, we envisioned something that would be like a kinesy tape, so electrodes that are integrated into the textile and that are stretchable and basically can be used as some type of a band. And the idea of this is that first to show you where this is the state-of-the-art technology, and then I can show you where we are with the Wearplex technology with this embedded OECT circuits. So what we have now currently, we have a functional prototype of the system that embeds this 3-to-8 decoder or demultiplexing circuits that Peter showed, that are still in characterization. So basically we don't have a functional demo here, but I can show you how the system, now current version of the system, looks and what are the components. So basically, if you're speaking about this 3-to-8 decoder circuit, this is how this is connected to the system, and this is the hardware that was developed by Technalia that embeds both the stimulation and recording capabilities. So inside of this box there is a 4-channel stimulation unit and also 4-channel recording unit. Clearly this is basically adding towards the shift that we envisioned with Wearplex technology, because idea is that now with this only 4-channel stimulation inside, we are able to drive all these 32 pads that are here. So basically, this is the idea of the Wearplex, and this is what you saw already in the demonstration and the videos that Milo showed related to the functioning of these circuits in both the stimulation and the recording. But other than this, what is interesting to show is that not only were we able to develop the functional, well, to the degree some of them are fully functional, but circuits that can be used for both of these applications, we also reach the level where this can already be embedded into the textile. So this is the same circuitry. It has all these OST printed logics inside, and it's now embedded into the textile. And we tested this and compared it. Well, like mentioned, these circuits were not initially fully functional. So let's say 7 of 8 of these outputs was working correctly, and you saw in the presentation for Milos, for some of them basically the current is divided between pads, and for some of them it works a little bit slower but can reach the targeted levels. And this is now with this textile integration we confirm that this works in principle because the circuits were not degraded in the process of the textile integration. This is the current state of the other circuit that you saw. It's the more complex 8-bit shift registers that is, well, mimicking this electrode for tens that I explained. So basically high density. And what is interesting in this electrode is that it's embedding this, well, we call it we call it basically the bus. So basically all the information channels are divided between these electrodes. What this allows us is to simply cut through electrode wherever we want. Once again, targeted application. Imagine this being basically a band-aid that is actuated basically with these electrodes, and you can cut it wherever you want, basically depending on the need, how long you want to make it. One more thing to mention is, of course, these electrodes that we developed, we were able also to integrate it with this electrode skin interface material from eDune, and this is now also being characterized in the functional test for electrical stimulation. And not only that, but also to show all these parts related to the primer layer. So this is the textile that has the primer layer that University of Southampton presented, printed on top, and then on top integrates all these circuits, and in the end the interface layer from eDune. So basically all the components are inside of this. Clearly it's still not 100% functional, but we are very close to getting there. It already resembles basically the complete system. So one more thing to basically showcase in what we were able to develop into this gamma stage is the human model equivalent circuit that was introduced by Nicola Perinka. And the idea of this is that we now have something that is based on the same technology as our multi-pad electrodes, but can be used for initially testing them prior to placing them on a human, because in this pre-printed circuit we have the same electrical properties as the human skin, and this allows us simply like having the electrode newly printed electrode like this. We don't need to place it on the skin to test it. We can use the human model equivalent circuit. The pad size is exactly the size of the electrode in our demonstrator. So simply placing one on top of another and connecting it to the oscilloscope, we have a system that can be used to basically characterize and, well, explore what would be the situation of the current distribution and the behavior of our electrode when it's placed on the human. So these are all the components, current components of the system and the overall system. Well, ideally, what we have already is that we have a compact system like this, the electrode that embeds all the OST logics to drive these 32 pads, and this four-channel stimulator that can be used for stimulation. And then when this is connected to the recording electrode, we have the same setup we have inside four-channel recording device, and we can already record from this 32-pad electrode that integrates the logics inside. So basically, reducing the size of the electronics of the conventional system that is hard, and having everything printed and integrated. This is the goal of Wearplex, and we believe we achieved quite a lot in these 3 years. That's the end of my demo, let's say.
Excellent, thank you, Mattia. So actually, one of the things just to add to that is so the huge advantages of this human equivalent circuit is that when we do start making, or if a company starts making huge batches of these, that they're not having to obviously test each individual one on lots of different people. You can test it automatically using that. So it's a really good breakthrough. So next up we've got, so it's our speaking of end users, so it'd be the Wearplex end user companies. They're just going to do a little presentation on their sort of future developments from leading off from Wearplex. So to begin with, it's Azada Motila from layer 1. So she's going to talk about the future reduced graphene ink development, reduced graphene oxide ink developments.
Can you see my screen? Can you see my screen, the slides?
Yeah, it's still on your view there. Oh, that's turned off.
It's okay now?
Yeah, that's it.
Okay.
Oh, let's switch back again. Seems to be
It's
a bit of a lag.
now, right?
Well, we can see your screen, but it's still on your editing view rather than. I think if you press F5, it should make it as a presentation view.
Yes, let me continue with this. Hello and welcome to today's workshop. I'm Azadeh from Layer 1 company, former Abolonix. I'll give you a brief information about our products and future RGO-based ink developments. Let me first explain more about GO and RGO. Graphene oxide, or GO, is usually synthesized by chemical oxidation and exfoliation of graphite by normally Hammer's method. And RGO is prepared by reduction of GO, removing oxygen groups using chemical or thermal conditions. In this table, you see the main differences between these two materials. One of the prominent differences is the electrical conductivity, which was sought in Wearplex project. GO is an insulator, while RGO or graphene is a conductive material. RGO has potential applications in different fields, including conductive inks for electronic applications. We have large-scale production of GO and RGO as 3 and 1 kilogram per day, respectively, and these photos belong to our former production site. Over 3 years of Wearplex project, we could synthesize different series of RGOs, which showed higher conductivities compared to our routine and normal one. In this table, you see a relative comparison between these RGO grades. As shown, those RGOs developed in Wearplex had 10 to 500 times more conductivity than our routine RGO. But we need high reduction temperatures, additional annealing step. We had low production capacity, which results in high cost. And we measure the bulk electrical resistivity of RGO powders with this setup. Well, Based on the R&D activities and the results we achieve in this project, we pursue 3 strategies for our material development. First, a new scale-up design for the production of Geo as the main precursor for RGO is under development. Our new owner, Aker, is now planning for industrial production. We are setting up a new line to increase the production capacity 12-fold with full automation, reducing the production cost to 1/4. Meanwhile, we are modifying Geo properties to have less defective and more conductive RGOs. This process is also under development. We are targeting conductivities more than 3 orders of magnitude, which can significantly improve our product portfolio. Moreover, since we are progressively working on improving electrical conductivities, in another approach, nitrogen doping of RGO was utilized, which showed promising results in ink formulation. We are preparing to scale up this grade as well. The project is ending, but if you would like to test our new materials, please contact us. We would be happy to provide you with our new RGO grades. It's almost finished. Okay.
Excellent. Thank you very much, Esther. So next up is Katya again from Eden Technologies, so talking about the future wearable biopotential applications.
Try to share. Okay, can you see the video player?
Yep.
Okay. So I'm going to show you a video now that has 2 parts. So before I already showed you in the presentation our EEG system for the ears. First in this video we will have a look at all the components and the hardware, and in the second part we will see a quick demo that we have realized together with a partner from the audio scene, maybe the audio field. Let's put it that way. And I will just talk over the video. Okay. So we have developed our Guardian. It's called development kit, and this is basically an unboxing video, but it's nice for showing all the components. So we have on the right side there the bridge. This is then talking to the internet, and this is the brain box, the smaller box. This will sit in the neck during the measurement, and it has electronics inside, an amplifier and so on. This is connected via Bluetooth to the bridge, and that's how we can connect basically the brain to the internet, or how we can get the data from the person to our web app where the data is analyzed and displayed. Yeah. So this is how you assemble the headset, basically. So we have the brain box, we have cables connected, and those cables are equipped with an earpiece which has little conductive PCBs that then establish the electrical contact between the electrode, which is the ear tip in the right here, and the electronics. And now you just put it in your ear like normal headphones. Okay, let me pause this here. So we created this little demo that you can see in just a second, together with a partner from the audio area, and that partner is creating a spatial 3D audio, and we can actually to control the audio quality, or let's say where the audio signal comes from, by looking left or right. And this signal is then picked up by our earbuds and controls the audio. So this is our test subject. He's actually our software developer, putting the Guardian in. And now when you can focus on the computer screen in the video, okay, there you can see him looking to one side and then to the other. When you focus here on the screen, the audio quality is displayed by those colored circles. And by moving the eyes to a certain direction, the audio is shifted to the direction you are looking in. Yeah, that's it. How do I get out? Yeah, and of course that's not all we can do. This is just a little demo. There are other applications. We are also investigating sleep monitoring at the moment, for example, with another partner. So yeah, thank you.
Okay, thank you, Katja. So next up is Jenny Isotala from ScreenTech in Finland, and she'll be telling us about their e-textile device manufacturing. You're muted at the moment, Jenny.
Oh,
there you go. That's it. Perfect.
Can you see my screen?
Yeah.
All right. So hi everyone. My name is Jenny Isotalo and I work as an NPI engineer at ScreenTech. And ScreenTech is a contract manufacturer in the field of printed electronics. ScreenTech was founded in 1989 and my topic today is e-textile device manufacturing. For over 10 years, ScreenTech has been applying its knowledge and experience in the field of printed electronics to manufacture custom disposable medical electrodes for both diagnostic and therapeutic purposes. These are some of the examples we can make. Use cases can be medical measurements, sport medicine, stimulation, wellness, and so on. And at ScreenTech, we are able to combine these measurements to accommodate innovative new applications. We can print electrodes to flexible substrates like PET and TPU, and thickness of TPU can be between 50 micrometers to 150 micrometers. And here are processes that we have in-house. Flatbed screen printing, heat and UV curing, lamination, mechanical cutting, laser cutting, dispensing, mechanical parts, assembly, and clean room. We have sheet-to-sheet as well as roll-to-roll processes. Sheet-to-sheet process allows us to test the design quickly, and later we can start to manufacture the product using roll-to-roll processes. We have printed on textile also. There are 3 printed layers in this textile electrode: silver, silver chloride, and dielectric. And in this Wearplex project, we tried to print OECTs on textile using our flatbed roll-to-roll printing machine. The manufacturing is done layer by layer, and when printing many layers, the alignment accuracy is very important. And for these OECTs, we printed 10 layers. And after every printed layer, the textile substrate moves through the camera system to be checked and recorded as a print image. So, start it again. Okay, I will explain a little bit about our camera system. There are 3 electrodes printed in the image on the left-hand side. 4 different layers have been printed: gray, green, yellow, and black. And when printing in flatbed roll-to-roll machine, the desired electrodes are printed layer by layer, and after every printed layer, the roll is taken again and put to the beginning of the machine to print the next layer. So in order to verify the alignment accuracy of the printed layers using the closed-loop camera system, the machine is equipped by a coding device that gives a code bar number to every sheet, and also by cameras installed after the printing area. The first layer have register marks. Other layers have small line added next to the register mark. This data of register marks from the first printed layer and those little marks from the other layers will help a lot in controlling and verifying the quality of the printed sheet. And with this system, we should know if the printed layers are in the right position and if they have the right distance from each other. And here you can see our results of the roll-to-roll printed OECTs on textile. And the picture on right-hand side has been taken on the light table, so the prints under Dielectric can be seen easier. And the question is if the alignment accuracy was good enough that these printed OECTs could work. We don't know that yet, but we have sent these printed OECTs to RISE, Sweden, and they will test them. And the functionality and overall performance of the resulting components are very much dependent on the alignment and patterning accuracy of every individual layer. And printing was slow because there are so many layers, and also the alignment accuracy was challenging. And we also need to do more improvements to the camera system when we print on textile. But we got some quite pretty prints of OECTs, but there are still challenges with repeatability and manufacturability. Thank you very much.
Excellent. Thank you, Jenny. Okay, so that brings an end to the talks and the demonstrations that we had. So the next stage, we're just going to do effectively go through any questions and answers session. So if you, I can see there's a few questions in the chat, and if you have any other questions, then please ask them now. Otherwise, I'll just share Steve's. Oh, there he is. Oh, sorry.
Are you sharing the slide as well, Russ?
Yeah, it should be. That's what I'm trying to click on. It's too many. I can't find things here.
Well, good afternoon, everyone. My name's Professor Steve Beebe. I'm from the University of Southampton, so obviously I work very closely with Russell. And yeah, this, as Russell said, this we've got 10 minutes now just to basically answer any questions you have. And it's also an opportunity for you to comment upon the research and the things you've seen here. So this is the workshop really is intended for us to sort of get information from you, as well as for us to obviously disseminate the results of the project. So some of you already put some questions into the Q&A box. So if you do have a question, please use the Q&A, the question mark, the sort of logo at the top, icon at the top, and I'll go through those. So we have got 4 questions here. So I'm not sure who in the consortium is best placed to answer this, but can we fabricate wet printed electrodes on a sticker? So I guess on a sticker we mean something that goes directly onto the skin. So this would be as opposed to dry electrodes. Who would like to handle that question from amongst the consortium? So to the best of my knowledge, it's very difficult to print wet because, well, when we print them, they are wet to start with, but then inherently you know, you normally dry or cure the electrode such that it stays on the substrate and is not removed. I think wet electrodes won't last terribly long. Anybody else want to comment on that?
Yeah, so I was just going to say, I don't know if he also meant by sticker. I wonder if he meant it like a bandage or plaster or something. So if that is the case, then yeah, that's something we're definitely looking into as well. Is being able to print onto various different surfaces. So one thing we can do with these materials, instead of using screen printing, another option is dispenser printing, other additive manufacturing like inkjet and so on. So you can print on a sticky or wet surface. Potentially, it obviously depends on how that surface goes, but yeah, it is possible.
Maybe one more comment. You can also print adhesive. So basically, if this is the task, you can print adhesive very precisely to add as a top layer.
Okay, so connected to this is, do you need to wet the electrodes for the EMG to reduce the noise? So obviously, conventionally, typically with the electrodes, they use a gel to improve the contact resistance. Is that necessary for the Wearplex technology?
Yeah, well, I can start answering this question, and then if someone wants to add it, feel free. So basically, this is the point of some of the developments that we are working on in the Wearplex project. So the idea was exactly to get rid of these wet electrodes, because they're not very much usable in daily life or clinically, right? Because even if you have something in the textile, and let's say that from the internal side of the textile, you have some sponge that you have to wet from time to time, and then you place this sponge, such an electrode, such an interface will work for a while, but then when the sponge dries out, you will have to do it again. So by avoiding these wet electrodes and by using more advanced technology that is coming from EDUN, for example, this dry skin electrode skin interface layer, we can have an interface which is basically convenient for clinical and daily life applications, as you could see in the demo. In this case, you take the sleeve, you wrap it around, and it stays there forever. You don't need to vet the electrode, and you have your application. And so far in our tests, we have some very nice results, and it seems that this contact and interface is quite stable, and we can use it to control different devices, as you could also see in the demo. Maybe Luis, you can share your experience working with these electrodes. Obviously, a systematic evaluation is coming out, and as Russell has noted in this webinar, we still have to wait a little bit until the publications are out, but so far the results are quite promising.
Yes, and just to a minor comment, not wetting the electrode, but it's always useful to actually clean the skin. So we kind of prepare the skin with a cream, so you need to remove the grease and so it's just in case. So it kind of helps always for dry electrodes, and it's just a smooth cleaning. It's the only thing that we just take care of, and then the electrode, we don't need to apply actually any moisture or anything else, as Straina just commented.
Okay, great, thank you very much. So again, following on from this, having established we're printing dry electrodes, we've got a question here regarding the thickness of the carbon layer for the roll-to-roll printed electrode. So how thick is that printed layer? So again, who's David, could you answer that?
Yeah, I can't answer that from memory. I would have to look into our tables and data to get the exact figures, but it's comparable what you get in flatbed sheet printing, as we use same screen materials for the roll-to-roll printing. You basically get the same as you do in conventional flatbed screen printing. But for the exact figures, I can quickly look it up and come back to you.
Could you give us just a ballpark figure? I mean,
Peter is here. I think it's on the order of 3, 4, 5 micrometer, depending on ink viscosity and mesh and so on, but that ballpark.
Okay, thank you, Peter. Thank you, David.
Yes.
So again, another question on regarding the printed. So the primer layer, is the primer layer compatible with any kind of textile? So polymer, cellulose, etc. So Russell or Abiodun?
Abiodun?
Oh yes. Yes, the primer layer is compatible with most materials, but obviously, if you're printing materials with cotton, for example, high fiber content, you would have to consider the roughness of this of the fabric you're looking at. But with most of the fabrics we've been printing on, it's very compatible, and you can achieve thin layers of primer deposition on them. But obviously, the rougher the substrate is, just like cotton, for example, or wool, you would have much difficulty, or a substrate like felt, for example.
Okay, thank you, Abiodun. So we haven't had any further questions, but in case or while we're waiting for any more to come in, a question for the consortium as a whole as a general point, and indeed for anybody watching in now. Where do you see the Wearplex technology being used first? So what's a horrible expression, but what's the lowest hanging fruit for the technology to develop into and be applied? And again, as I say, anybody out there watching the workshop, you're very welcome to comment on this as well. So I think different members of the consortium. Different members of the consortium might have different views on this. It would be interesting to hear it.
So I think one of the low-hanging fruits we have identified, I think, on the EMG side, because there we could really approach, or we had the least obstacles now during the project in terms of this integration of electronics with the electrodes. So I think that's really an avenue that I consider we reached probably the lowest, the highest TRL, technology readiness level, towards the end of the project. We have very latest this new materials that have been used by RISE that probably will make it also much more feasible to use it for electrical stimulation. But we were running a lot into these issues of not being able to have enough current produced for really functional electrical stimulation requirements when the voltages are getting very high due to the skin interface. And this is definitely not an obstacle that we observe when we are using it for the electric myogram recordings. So I think that's really the lowest hanging fruit what I could see now that with all these results we could achieve.
Thank you, Thierry. So I mean, there's another discussion point we've got on the slide there. Does that also relate to the biggest market opportunity, or would another application represent a bigger market opportunity?
I can give a quick comment, Stevie. I just also want to emphasize that it's the right time for this technology. In particular, with respect to these EMG recordings and myoelectric control, because traditionally myoelectric control was mainly associated to rehabilitation, where basically you have this interface, and in this brief presentation I have also shown some scenarios where you use EMG to control a prosthesis or an exoskeleton, or you can use it commonly in the rehabilitation of stroke subjects and so on. So medical applications were mainly in focus, but recently, from a couple of years, you can see that the interest for using myoelectric control more generally as a general human-machine interface is actually increasing. And this is also why we have commercial devices such as my armband and this band from the Control Labs coming out on the market. Because it's also quite attractive interface, you don't see it, right? And obviously you can capture hand movements and wrist movements by putting a glove, kinematic glove on the hand. But then you also impair sensations and you have to wear something. So this EMG sleeve is a kind of a contactless interface that can be quite convenient for general purpose applications, especially when we think about interaction between a human subject and digital technologies, this popularly called metaverse and collaborative robotics, industrial robotics, and so on. So I think that it's a fruitful market that is now probably is gonna boom in the next several years. That's the expectation, at least.
Excellent, thank you, Trina. So I think we're running out of time now. So we've got just under 5 minutes left. So I think it's over to Thierry for the closing of the workshop.
Yes, okay. Perfect. Yeah, thank you. Thank you for putting up the slide. So it's an honor for me to give the closing remarks here, although it's also with one wet eye, because that also means for us, we are also about closing the project. And I think we have seen really main and big achievements that we could make on all these printing technologies, the printed circuits on the inks, on the interfaces that really led about to get into tangible demonstrators. And we are a little bit running out of time on that, which of course is always also then a call for going into new ventures, into new projects, into bringing now these TRL levels that we could significantly increase, because we have started basically on an idea. So normally when you say we start on an idea, then this is a TRL 1, where we did all the kind of basic research of putting things together in the context of really using this technology, this printing technology, for introducing electronics into electrodes. And what the consortium could achieve here is really remarkable in terms of getting the structures small enough that we could get on these sizes of the single electrode pads and having this multi-layer electrodes. Of course, in terms of scaling up and ramping up the technology, there are still a lot of challenges that are remaining, and this is regarding the print size, because with screen printing technology and with the sheet to sheet process, we could have really the small structures that we are struggling to have in a roll-to-roll process. So we would like to go even smaller in making these OECTs circuitries that then we can put them into the exact scale of the electrodes themselves. So here we have identified a big challenge. We have identified the challenge on how much current can we introduce or put through these electronic circuits, and only in the very last few months we also found solutions how we can do that. So it will be very interesting and very important to have a continuation on these developments. In terms of applications, I mean, you have seen a number of applications also that the companies have developed using the fruits of this technology. And what we have identified is really as an application, as I just mentioned before, this high density multi-channel EMG electrode with integrated electronics. Then we have also identified that we can use, I mean, when we use electrical stimulation with low intensities, we can use them very efficiently for electro-tactile stimulation, which again goes into this area of extended reality in this direction. So I think the consortium can think about that, and I hope also some that are here in the audience could see that this can be a good direction in pursuing this integration of the demultiplexers, multiplexers with electro-tactile stimulation. And then multi-channel iontophoresis is also a technology where we can handle or get results with low currents. And as we have seen the special interest on this, what I call an active tape, so stimulating tape that can be used for TENS application for this, for example, for pain applications. That can be another direction. So I would like to, next slide, Russell. So I would like to motivate everybody that is here to go through this list here where we have the partners and to contact us with ideas, with potential future opportunities that we could take from the consortium to really move this technology to the higher TRLs. I think there are opportunities when we look at the different work programs. We still do not have a full picture on the medical devices work program that is about to raise or to come out, but I see there for medical devices having electronics integrated electrodes is definitely something that that for the future has a very high potential. So with these closing remarks and with the call for joining and connecting to us, I would like to close this webinar and thank to all the audience, to all the presenters, to all the team here in Wearplex for their contributions and their interest in that project. Thank you very much. And I think Russell can officially close the webinar.
Excellent. Thank you, Thierry. So just to quickly say thank you very much, as Thierry said, thank you for everyone for coming and thank you for all the presenters. Just say so. Please keep an eye out on our website. So as we've shown here, there's a few things that we're still finishing off. So there will be some publications hopefully in the next few months. So that we'll put some more detail up on the website. Equally, if you join our email list, then we can email that out as well. But otherwise, just look on the website. For the video, there's a few people asked whether this will be recorded. So it is recorded, and I believe as soon as I click end on this, I'll probably give it an hour, and it auto generates a video. So when you click on the link to join this webinar, it should now be a video, but I will actually make that available as well. But as we've got 6 deliverables due by the end of the next week, then there might be a slight delay on that, maybe the week after. But yes, again, thank you very much, and yeah, thank you to everyone. So we finished.
Thanks, Russ.
Okay, thank you.
Thanks, Russell. Thanks all.
There's a way of showing all of us.
Thank you, Russell.
Thank you. Goodbye.
Thank you, everyone, and thank you, Russell, for the great organization of today's workshop.
I was just seeing if I could get a picture of all us up. I don't think we can on this. No.
Not on this mode, I don't think.
No. Okay. Thank you anyway.
Thank you very much.
See you later.
Goodbye. Thank you.
Bye.
Thank you. Bye bye.
Cheers. Bye.